We've already looked at indices or index numbers or exponents, and now we move on to looking at logarithms. Logarithms are just indices of special base numbers. These base numbers are usually base 10 or base E. Now, if we're going to talk about base 10, we just call these common logs, or just logs. We don't need the word common, just logs. If we're using E as our base, we're going to talk about natural logs. And we're going to use the expression Ln. Now remember, this E is a special number, it's Euler's number, and it's approximately equal to 2.72. So it's just a number, just like 10 is a number, so is E. Now, on our calculators, we've got two buttons. We've got a log button there, and then we've got a natural log button there. So we will use both of these as we go through. In maths, we have a lot of operations that are opposite. We have plus and minus, we have times and divide, we have to the power of and to the root of, and logs and powers are the same kind of thing. If we asked ourselves, what power of 2 we kind of know that, but let's write it in a different way. Let's write it as log to the base 2 of 32. Those two statements are the same. What power of 2 is 32? We can write as log to the base 2 of 32. The answer must be 5, because if we look at it the other way, 32 is equal to 2 to the power of 5. Let's have a look at another one. Let's ask ourselves, what power of 4 is 16? We know the answer, but let's write the information in a different way. Let's write it as logarithm to the base 4 of 16. Okay, so we know the answer. We know that what power of 4 is 16? The answer is 2. So log to the base 4 of 16 is 2, because 16 is equal to 4 squared. Some slightly harder ones. What power of 5 is 1 over 25? Well, for a start, it must be negative, because it's 1 over, and 25 is 5 squared. So the answer must be negative 2, because 1 over 25 is equal to 5 to the negative 2. And it's this that is what we're calling the log. But as you can see, this is just the power as well. So they're all inextricably linked. Right. Log to the base 7 of root 7 is what? Well, that's asking us what power of 7 is root 7, and the answer is a half. And the reason that's a half is that root 7 is 7 to the power of a half, and it's that power that is the answer to our question. What power of 7 is root 7? We know the statement that this is true. 36 is equal to 6 squared, where 2 is the power, 6 is the base. So we can write that exactly the same statement, just looking a little bit different. Logarithm to the base 6 of 36 is equal to 2. Similarly, we know that 64 equals 8 squared. 2 is the power, 8 is the base. So we can rewrite that and this other notation of log to the base 8 of 64 is 2. Same again, we know that 36 is 6 to the power of 2, so that we can write the power to the base 6 of 36. It's not a terribly mathematical expression, so we can cross that out and write log, or logarithm to base 6 is equal to 2. It's still asking us that question, what power of 6 is 36? Something we need to remember, if we think about something like this, log to the base 10 of 10 squared is equal to 2. So 10 to the log to the base 10 of 100 is equal to 100. Actually, we could rewrite that and we could say log to the base 2 of 100 is equal to 2. Another way to remember this is just to think of the meaning of it and to think of which bit goes where. The x is the answer to the question, what power of a is n? So a to the power of what is n? So x is the answer to the log. Log to the base a of n is x. These statements are equivalent. Because logs and powers are so closely related, it shouldn't come as any surprise if we now break them up. If we find the log of a product, we shouldn't be surprised to see that we can call that a sum. Similarly, the log of a quotient is equal to the subtraction of those quotients. And thirdly, the third law of logs, we can use, the third rule of indices or powers, we can use here its multiplication. So the log of x to the power of m will be m times that log. Now, we're not always going to get things that we can look up on the calculator. On the calculator, we can look up base 10 logs and base e logs. But if we have some question that's not of those two bases, then we can't use our calculators. Classier calculators can, but not the ones that we're allowed to use. So we have to use this base change formula. And it's very simple to use. Suppose we want to find log to the base 3 of 40. What we're going to do, it doesn't matter whether we use 10 or e, as long as we're consistent. So let's just use log to the base 10. And remember, if we've got log to the base 10, we don't have to write it in. So that would be log 40 over log 3. And then if you needed to, you could work that out. It is really important to be able to manipulate things. So we need to be able to simplify something that looks a bit like this. So 2 log x over y plus 3 log y over x. Okay, let's simplify that. First up, we can shift the 2 so that we have log of x, y squared plus log y over x cubed. Now, using the first rule of logs, we can see that this is going to turn out to be a product, so it would be log of x over y squared times y over x cubed and x squared over y squared times y cubed over x squared will give us that the answer is log of y over x. Y equals 10 to the power of x and y equals log to the base 10 of x are inverse functions. Similarly, y equals e to the power of x and y equals log to the base e of x. They are also inverse functions. So if we're drawing inverse functions, you know that they are reflections in the line y equals x, which is the mirror line here. So if we first up draw y equals 10 to the power of x and then reflect it in the line y equals x, then we get y equals log to the base 10 of x. Now look over here, this is log to the base e of x, and remember that e is equal to 2.71 something or other, and this one is log to the base 10 of x. So the smaller the base number, the more up the curve goes. So the shallower it is the bigger the number.